In this video I'm going to talk about parametric and implicit plotting. So to deal with parametric plotting, that's the case where you've got your x and your y, and x and y are both given in terms of some other variable t. So here's an example. Okay, so we start with 1,000 points between 0 and 8 pi, and so x is going to be t minus sine t, and y is going to be 1 minus cos t. And then we're going to plot x against y. Okay, so you get this picture like this with these kind of hoops, but this is actually kind of a bit misleading, because if you can see there's kind of the vertical scales going from 0 to 2, and then 0 to 2 along here is just that, like just a short bit like so. It's got different scales on the x and the y axes, and for this particular example that's kind of not helpful. It's better to have same scales on the x and y axis. So we can just do plt.axis equal. Okay, that's a keyword that we need to make the axes equal, and there's a now we see that we've got these like hoops, but much smaller, and let's also just kind of put in the horizontal, put in the x-axis. So we had in the previous video we had a method for sort of moving the spine from the bottom down to the middle, but here let's just instead of doing that, we'll just use a different thing. We're going to do blt.h lines, so that's going to give us horizontal lines. Okay, so so it's actually okay. Let's just hover over here and see what it says. So firstly, the first argument is going to be the y value, the height of our horizontal line, so we're taking that to be 0. And then you've got an x min and an x max. So the x min is the sort of left-hand end of our horizontal line, and the x max is the right-hand end. And we're going to go from 0 to 8 pi. And let's do it like this. We'll do r dash. Oh no, okay, actually that's not going to be valid here. We have to okay, we have to do this slightly different. Okay, so we'll do color equals gray, and line style dot dash. Okay, so now we're going to get a dashed horizontal line at height 0. So what's the point about this particular curve? I mean, this is actually, if you imagine a rolling wheel. Okay, you've got a rolling wheel, and you mark a point on the edge of the rolling wheel, which kind of, you mark a point on the edge of the rolling wheel that's just next to the ground when you start, and then you start rolling the wheel. Then your marked point on the edge, after a little while it'll come up to that point will roll up to be at the top, and then a little while later it'll roll back down to be at the bottom. And you can check that it actually forms this kind of pattern. As the wheel rolls, that marked point traces out this curve here. It's called a cycloid curve. Okay, so that's one example of parametric plotting. Okay, let's do another one. Okay, so here, I mean, for this example, t is kind of morally supposed to be running from minus infinity to plus infinity, but we can't do minus infinity. We're just going to, so we'll do some reasonably large number. I mean, 8's going to be good enough for the minute. Okay, and so x is going to be 1 minus t squared over 1 plus t squared. And y is going to be 2t over 1 plus t squared. And again, we're going to make the axes equal. So we've got the same scale on the x and the y axis. And so we find that what we've got appears to be a circle, okay, which is slightly curious. Well, and if you're curious about why that is, well, you can go away if you can see if you can remember some stuff about the formula for sine theta and cos theta in terms of tan half theta. And once you've remembered that, you should be able to understand why this is actually a circle. So that's another parametric plot. Okay. As well as parametric plots, we sometimes want to do implicit plots. Okay, what do we mean by implicit plot? You know, that's where we know some relationship between x and y, but we don't have actually a specific formula for x in terms of y or y in terms of x. Okay. Okay, so we're going to do an example here. So we're going to consider a function. Let's maybe just define it as a function here. Okay, so there's a function f of xy is y squared minus x cubed minus x, and the curve that we're going to be looking at is the curve where that's 0, where y squared is equal to x cubed minus x. So that's kind of not there's no really very tidy way to give yourself a formula for x in terms of y or y in terms of x based on that. But instead, so we need to just kind of look. You need to search over the whole plane for points where this is 0. So what we're going to do is we're going to make a mesh of values. So we're going to have our x values. We're going to call this xr for this is the row of x's. That's how you should think of that that r there. It's okay. So let's just do. Temporarily, let's just do 4 points between -2 and 2. Well, actually, let's make it 5 points, and the same for y. Okay, so 5 equally spaced points. So here your YR is just the numbers -2 up to 2, and your XR will be the same. That's kind of somehow not quite what we want. What we're going to do is we're going to use this np.meshGrid thing. Actually, let's call this YC, right? This C for column, R for row. Okay, so let's now see what what this does for x. Okay, so x is now a 5 by 5 array. So this is kind of giving you the x values at every point, right? So we've got like a 5 by 5 grid, and everywhere in the first column, everywhere over here, x is -2. Everywhere here, x is -1. Everywhere here, x is 0, 1, and 2. Okay. Whereas if we look separately at y. So y, these are all the y values. It's a 2 by 2 grid of y values. On the bottom row, it's always equal to 2. Here it's 1. Here's 0, -1, 2. Okay. So so we started with a kind of one-dimensional row of x values, a one-dimensional column of y values, and then we've kind of combined them into this kind of grid thing here. that's what we need to do. And then we're going to look at these values here. Actually, we can just do it like this. Z is f of x, y. Okay, so here's all the values of this fxy at all these various points. But actually, so we're not going to be able to do anything with only 5 points here. We'll do 500 instead. Okay. So now we want to plot contours. So we do x, y, and z. So and then we're just looking. We just want to plot the contour where z is 0, right? So we, if we wanted to plot, where z is 1 as well, then we could just do 0, 1. But we just want to know where z is 0. Let's make it red. Okay, so here these are all the points where our z is equal to 0. You can see that so this is what's called an example, what's called an elliptic curve. You see you get like a closed curve here that's quite close to a circle but not quite circular, and then there's this arc here, and in fact this arc kind of runs out to infinity in both directions, but we've only shown part of it. Okay, so that's one example of an implicit plot. We'll do another example. Okay, so this I'll do a different function. Let's call it g. So okay, so this function g is x sine x squared plus y squared minus y cos x squared plus y squared. And again, we're going to do, we need to make a grid, so we're going to do this. We're going to do we're going to do 1,000 points between -5 and +5 for our x values. And the same for y, and then our so as before, these are one-dimensional arrays, and we need to kind of make two-dimensional arrays with kind of replicating xr as each row, or replicating yc as each column. Okay, so notice actually this is quite big. I mean, we've got 1,000 rows, 1,000 columns. There's 1 million entries in this mesh, but fortunately Python can deal with this pretty rapidly. Okay, so then we're going to do we're going to do two plots. We're going to do two plots side by side. So we'll do. So, sorry, I wanted this to be 1, 2. I just want 1 by 2, like so. And then the left-hand plot. I'm just going to make sure that that's got the same x and y scales here. Both going to do that both on the left and the right, and then we're going to do. Okay, we're going to look for. We're going to plot where this function g that we defined up here. We're going to plot where that's 0. I'm going to plot that in red. Okay, so we get this funny curve like this. But why have I done two things? That's because, in fact, we can make the same plot parametrically. It's a little bit of interesting mathematics to check that this works out. So let's actually put the definitions back here. I'm going to define a function. Find u of t as t cos t squared. And I define v of t to be t sine n beta, sine t, t sine t squared. Okay, so now on the right hand side. We'll again set the x and y scales to be the same, and then we're going to let t run from -5 to 5, and then we're going to plot u of t and v of t. Okay, and you see that you actually get the same result, right? So the locus, the place where this function where x sine x squared plus y squared is equal to y cos x squared plus y squared, that's precisely the set of points of the form u t v t, where u and v are given by these functions here. Okay, so that's some examples of parametric plotting and some examples of implicit plotting, which will be enough for this video.